Hi everybody and welcome to this new release webinar, LedaFlow 2.11. My name is Ludivine Roswell and I'm the LedaFlow product owner at Kongsberg Digital. During this webinar, I'm going to present you some of the latest improvements in LedaFlow, first on the models, then on the performance, and finally on the user experience. I will make sure to keep some time at the end to answer your questions, so if you have any questions, please post them in the chat during the presentation and we will go through them together at the end. I'm now going to turn off the camera. This is to ensure that you have the slide on full screen, but I will turn it on again when we come to the questions. I guess that most of you who are attending today already know a bit about LedaFlow, but I thought I would use 1 minute to introduce the LedaFlow products and their applications in case there is someone who doesn't know about them. LedaFlow is indeed a suite of several products. First in the list is LedaFlow Engineering, which is a desktop application allowing you to run transient simulation of multi-phase flow. Then we have the LedaFlow Point Model, which is a steady-state plugin that can be used by third-party steady-state simulators, and it is also delivered together with LedaFlow Engineering. The third product is LedaFlow Integrated, which has a published standard API that currently links to Kongsberg's Dynamic Process Simulator KSpice and CMG's Reservoir Simulator GEM. It also makes it possible to leverage cloud-native simulation through Kongsberg Digital Twin technology, CogniTwin. This is what we call CogniTwin simulation. All these products have originally been developed for oil and gas applications. However, we see a growing interest in using LedaFlow to simulate other types of fluids, for example, CO2. And due to the strong physical models that make LedaFlow, the software is very much suited for these new applications. If you're interested in knowing more about LedaFlow, please visit our website, ledaflow.com. Let's have a look at the latest model improvements, which in LedaFlow 2.11 are mainly related to CO2 modeling. If you have attended the webinar for LedaFlow 2.10, you already know about the CO2 flow project. This project was established in 2022 with the ambition to overcome some of the modeling gaps identified through a previous project called CO2 FACT. Most of these gaps were related to the modeling of CO2-rich flows, what we call CO2 with impurities. And in LedaFlow 2.10, we introduced a new model that improved the modeling of pure CO2. LedaFlow 2.11 now offers a new model for CO2 with impurities. This new model can be viewed as an improved version of the existing composition tracking model in LedaFlow in the two-phase region. So that means inside the phase envelope. While the enthalpy-based phase change model that was developed earlier in the CO2 flow project and released in LedaFlow 2.10 is used outside the phase envelope in the single phase region. That's what I've tried to illustrate here on that drawing. So let me remind you about those two models. The mass transfer for single components was revised in LedaFlow 2.10, as I said, and it is now based on a local enthalpy balance in each zone. This enthalpy balance can be used to directly calculate the local phase split according to thermodynamic equilibrium. What is a zone? A zone is defined by a continuous phase and the dispersed phase it includes. So, for example, either continuous gas and the liquid droplets or the continuous liquid and the gas bubbles. The gas and liquid zones are treated completely independently since the phase change converts continuous to dispersed phase and dispersed to continuous phase. This means that there is no direct interaction with other zones which have different temperatures. So that keeps the implementation relatively simple and it increases the numerical robustness. So again, this is the model that is used outside the phase envelope in the single phase region. Let me remind you now about the diffusion mass transfer. In LedaFlow, we use a non-equilibrium formulation which means that we don't flash the contents of each cell. We only flash at the inlet and for the initialization. The rate of mass exchanged is instead based on the following: a chemical equilibrium at the interface between the phases. That's this G value that you see on the illustration. The available surface area between the phases, the diffusion coefficients for each component, and the concentration in each phase. Even though the CO2 with impurities model builds on the diffusion-based mass transfer from the standard composition tracking model, there are some noticeable differences that I'm listing here. First of all, there is no actual diffusion in the CO2 with impurities model, while there is in the standard composition tracking model. The CO2 with impurities model only has mass transfer or phase change within each zone, never between zones, which is the case with the standard composition tracking model. It is also well known that third-party PVT packages can give unphysical and discontinuous results for the properties of vanishing phases. For instance, the gas properties in the pure liquid region. These PVT properties might be needed during the solution of the equations in case we have not yet removed all of the vanishing phase. So smoothing and extrapolation of the properties for vanishing phases or non-existing phases has been implemented in the CO2 with impurities model, similarly to what was done for pure CO2. This is important for the convergence of the equation system. The CO2 with impurities model uses a new explicit solver for the composition equation. This solver always solves the composition equations inside the hydrodynamic loop, while the standard composition tracking model solves the composition outside the hydrodynamic loops after the other equations have converged. So I've made an illustration to explain that. So this energy inside hydrodynamic loop, this option was introduced in LedaFlow 2.4, so that's maybe something that you are used to. For the standard solution, the standard composition tracking, as you can see, we have the energy equation that is outside of this loop. The hydrodynamic loop is represented by a red arrow here. For single components, we have introduced, as I said, in LedaFlow 2.4, this energy inside hydrodynamic loop option, which means that we solve the energy equation together with the mass equation and momentum equation. This has been done because CO2 cases can be very difficult to converge because the density depends strongly on the temperature. For the CO2 with impurities model, we saw that we needed also to solve the composition tracking equations inside this hydrodynamic loop. So that is the difference between the CO2 with impurities model and the composition tracking or the standard composition tracking model. As mentioned on the slide presenting the CO2 flow project, the development is either based or validated using the de facto experiments. However, data from CO2 with impurities is not yet available. So in the meantime, the CO2 with impurities model is tested against CO2 fact data. The model shows a good match for the temperature and the flowing gas mass fraction downstream the choke valve compared to a pH flash for the wellhead choking case, if you know about the CO2 fact data. The new CO2 with impurities model has also been checked against the single component model for pure CO2, which has been validated. And we also check for consistency against composition tracking. I'd like to mention a couple of improvements we have implemented for pure CO2. The consistency between the steady-state preprocessor and the dynamic model has been improved after we tightened the convergence criterion for the steady-state preprocessor. The phase change has also been improved in the cell immediately after the choke valve. Before we move to improvements that are not related to CO2 modeling, I would like to briefly explain how you would set up cases to model pure CO2 and CO2 with impurities in LedaFlow. First of all, in both cases, you need to create a multi-flash PVT object, as the single component model doesn't support PVT sim yet. So then when you have created this multi-flash PVT object, you need to select CO2 as the only component in your composition. And this will automatically enable the single component model. We recommend you to use the CO2 pure equation of state. And then remember that under case setting options, you need to enable the solve inside hydrodynamics loop option. So this is for pure CO2. And to set up a case for CO2 with impurities, it is very much similar. You also need to have a multi-flash PVT object. You will have, of course, a composition that has more than one component. We recommend you to use either Gerg or Peng-Robinson as the equation of state. Yeah. The most accurate results are obtained using the Gerg 2008 equation of state in multi-flash, but it can be quite slow, especially for a large number of components. So when calculation speed is important, then Peng-Robinson gives the best results compared to the other standard equation of states. Please note that the Gerg 2008 require an additional license from multi-flash. It is not part of the multi-flash basic license. And then when you have all this, you need to enable the model called CO2 with impurities, as shown on the screenshot here. And finally, remember to select the option solve inside hydrodynamic loop. I thought I would mention also some improvements that we have implemented for Steam PVT. First of all, regarding the initialization. So we now use a pH flash to determine the phase change, which makes it consistent with what is done for other single components. Previously, the steady-state preprocessor would return an error when it detected phase change. So that is if you use the steady-state preprocessor as the initialization option. If you use the gas filled pipe mode, the holdup is now determined from the temperature, which is consistent also with other single components. Previously, it was set to 0, and the temperature was set to the saturation temperature plus 10 degrees. We have also improved the steam density correlation and verified it against the YAPSW correlation. Note that this increases the gas density, which may result in a higher liquid holdup. So if you compare cases with previous version, you may see a difference in the liquid holdup. After these model improvements, I would like to mention some improvements on performance, because the parallelization has been improved for slug capturing cases that are using the new solver. That is something that we always work on. So during simulations, LedaFlow divides some computational calculations into parallel threads for faster processing. And we analyze how the equations are evaluated and solved in parallel, targeting those with lower efficiencies. What we have achieved this time is a speed increase of 3 to 4% compared to LedaFlow 210. So that's what you may see in this drawing here, or this graph here. We normally compare against 2.8 as this is our reference version. The efficiency has also increased a bit. So for 2 threads, we are now achieving an efficiency of 90%, and for 16 threads, an efficiency of 40%. Finally, I would like to mention a new addition. We have implemented a Python interface for the point model. This one comes in addition to the Excel interface. This is to give you more possibilities to plot or automate your analysis. Some people prefer working in Excel, others in Python. So now you have both options. Please note that this is independent from the Python API that is used to extract simulation results from the steady state dynamic simulators. That is all what I wanted to show you about LedaFlow 2.11. Thank you for your attention.